Okay, this video should be short and sweet. We're just going to talk about something that I hinted at in the previous video. Second and higher order derivatives. It's just when we take the derivative of a derivative and so on. So here's the deal. What we've been discussing so far, the derivative, we're now going to refer to that as the first derivative. We call it derivative for short, no problem. But when we have problems where we're dealing with more than one derivative, we're going to specify that that's the first. Therefore, the second derivative of f of x, that's just the derivative of f prime. All right, and we use lots of different notations for it. We can have this one here. The book reads that as f double dashed x. I say f double prime, and then we've got y double prime. And this one here is pronounced d2 by dy squared. And it's kind of a big deal that that's an x squared because, well, again, a dy by dx or d2y by dx squared, it's not a fraction, but it is kind of a fraction. And we've talked previously about the derivative being the instantaneous rate of change of the original function. And the natural example for that, in my opinion, is if you were to consider a position time graph. The derivative, the instantaneous rate of change of position with respect to time, is velocity. And the instantaneous rate of change of velocity with respect to time is acceleration. And the units for acceleration are meters per second squared. So there's a little connection here to physics. Again, we're going to talk more physics when we get up to chapter 23. But I just wanted to hint at that for the moment, especially those of you who are taking IB physics, you should already be familiar with a lot of these concepts. Okay, so we're asked to find a second derivative. We just do it in two steps. First, we're going to find the first derivative using all the rules that we know, product, chain, whatever the hell we need. So here we go. We simplify that. Great. And then to take the second derivative, we just take the derivative of this thing and we apply whatever rules we need to that. And in the end, we have an answer. Now we've seen previously that we can calculate the value of a derivative of a function pretty quickly on our calculator just by choosing this option. You just type in whatever value you want x to take on and then tell it you want the first derivative. Well, we can also choose the second derivative, and that's all you got to do, and then type in your function and you'll get your answer. You can't do higher than second derivatives on this calculator, unfortunately. You can actually go back into the function and change the order of the derivative, but if you type something in here, it's going to tell you, no, can only do first or second. You need a CAS calculator to do anything more exciting than the second derivative, unfortunately. Speaking of higher order derivatives, let's talk about the notation for it. If I'm doing a third derivative, I'll write down f triple prime of x or y triple prime. But beyond that, it just gets kind of ridiculous to keep drawing these dashes in. So the notation is going to be to put the derivative value that we want up here in parentheses. That way we know that this, for example, means the fifth derivative of x, not f of x raised to the fifth power. And if we're using dy dx notation, then just put the value of the derivative in where the 2 was previously. So for example, we've got f of x is cosine of 2x. We want to calculate the third derivative, evaluate it at pi over 8, and hopefully we get 4 root 2 out as an answer. This is easy enough. There's our function. We take its derivative, use the chain rule. Great. We take the derivative of that, use the chain rule again. Awesome. We take the derivative one more time, chain rule again. That's our function. Now we're going to put in pi over 8 into that and then figure out, simplify. Okay, sine of pi over 4, I know what that is. Let's simplify that and we, ta-da! Something worth mentioning, anytime that we have a polynomial function and we take its derivative, we're going to get a polynomial of 1 degree less because the constant term is going to drop out and go to 0. The linear term is going to become constant. The quadratic term is going to become linear, and so on down the line. The nth degree term is going to become an n minus 1th degree term due to the power rule. So first of all, if you're ever asked to sketch the derivative of a polynomial graph, you should be able to predict what the derivative graph should look like based on the degree of the original function. And secondly, recognize that this means once we take the nth derivative, we're going to be down to a constant. right? If we had a linear function and we took one derivative, we have a constant. If we have a quadratic function, we take two derivatives, we're at a constant. And that means that for any polynomial function, once we take the n plus 1th derivative, we're at 0. And there's no sense in taking any further derivatives than that. And thinking in this way allows us to answer problems like this, which looks like it would have been like an AP multiple choice question maybe. So we've got a pretty wild looking function. Obviously, we're not going to take the derivative 100 times to answer this question. So what do? Well, the 100th derivative is going to be a little bit easier. We look at this function, and if we were to expand it, this is going to give us an x to the 70th. This is going to give us an x to the 22nd. And then that's an x to the 7th. So when we multiply through, the largest degree that we're going to get out of this is going to be x to the 99th. And there'll be whatever, a whole bunch of stuff after that. So we know that when we take the 100th derivative of a polynomial of the 99th power, we're down to 0. So now the 99th derivative is going to be some constant. What constant will it be? Well, remember that when we take the 99th derivative, all of these other terms will have canceled out because they'll be coming from x to the 98th and below. So we only need to consider what happens when we take the derivative of this term 99 times. Well, when we take the first derivative, we're going to have 99 times x to the 98th. When we take the second derivative, we'll have 99 times 98 times x to the 97th, and then the third will be 99 times 98 times 97 times x to the 96th, and so on. So what constant is going to be left over when we take the 99th derivative? It will be this long product out here in front, which is going to be 99 times 98 times 97, and so on and so on. That's equal to 99 factorial. Quite a large number. I have no idea what it is. We're going to leave it in factorial notation. So this one is really cool. So we have the product rule, which we know fg all prime is equal to f prime g plus fg prime. And now we're going to take the second derivative of that product. And so that's going to give us a product rule from this and a product rule from this. This is going to give us f double prime g plus f prime g prime. This will give us f prime g prime plus f g prime. We can combine like terms in the center to get this. And some of you may already spot what's about to happen when we take the third derivative. It's going to be a whole bunch of product rules again. You can check the work down here. And again, when we combine the like terms, we get this. And do these coefficients look familiar now? Perhaps you want to pause the video right now and make a prediction as to what the fourth derivative of f times g is going to be. Here comes the answer. I'm not going to show any of the work, just the final answer when we combine the like terms. Yes, the coefficients are 1, 4, 6, 4, 1. These are binomial coefficients. I love it when mathematics comes together from different areas. So good. Here is the general form for the nth derivative of a product. Not that you need to know it, but I think it's really cool. And last thing, we have the limit definition for the first derivative. So naturally we can extend this and give a limit definition for the second derivative. It's just instead of f's up here in the numerator, we'll have f primes. We can also give a limit definition for the second derivative in terms of the original function. It looks like this. I've never seen a question on the AP or IB use these. The IB, I really don't think would. AP might give you something like this in a multiple choice, but again, I wouldn't worry too much about knowing this, just some fun facts for you. So the first derivative tells us the slope of the tangent line to a curve at any point, or let's say that differently, it tells us the instantaneous rate of change of y with respect to x. What does the second derivative tell us about the curve? And we're really going to focus on this next chapter. I just want us to start thinking about it now. So here's a parabola, and here's a stretched parabola. It looks like the tangent lines are going to have steeper slopes. Great. So let's just look in between, say, -1 and 1 for a moment. Here, look at where the y values are at. They're around 1 each. I suppose I can make them exactly 1. There we go. As my parabola gets stretched, the y values at both -1 and 1 are both stretching upwards, which means that the rate of change of y with respect to x must be greater when my parabola is stretched, because the y value has to change much more rapidly, right? You can just see that thinking about going from -1 to 1. Now it's changing from roughly 5 down to 0 and then back up to 5 again, whereas before it was just from 1 down to 0 and up to 1 again. And this is captured in our derivative graph. So back here, we can see, again, if we just look at 1, say, there's x value of 1, the y value on our derivative tells us the slope of the tangent line of the original function. So right now, that's at 2. Once my function gets stretched upward to whatever, now the slope, again, at x equals 1 is whatever, something like 7.5. Now those tangent lines themselves, their slopes are also changing, right? You could imagine going back here. So we have a slope at -1. Our slope is exactly -2, and our slope at 1 is exactly +2. So those slopes need to change from -2 down to 0 and then up to +2. And our steeper parabola, our slopes are steeper, changing down to 0 and then steeper again. So the slopes of the tangent lines have a rate of change, and that is captured in the second derivative. That rate of change is greater as our parabola stretches upward. In this case, our second derivative is a constant function because we started with a quadratic and we're taking 2 derivatives, so we're down to a constant. Anyway, we're going to think more about this in the next chapter. I just wanted to throw it out there, like I said, to get your brain thinking about these ideas in advance of having to really focus on them. So yeah, that's like kinda it. We'll talk more about higher derivatives in chapter 18 when we really focus on their graphical significance, and we'll talk more about them in chapter 23 when we see how they apply to physics. But for right now, you take the derivative, you take the derivative again, you take the derivative a couple more times until you figure out whatever derivative you need for the problem. Don't forget to use the chain rule every step of the way. And if it's a calculator problem, don't forget that you can do the first and the second derivative, evaluate it at a point very quickly there, rather than wasting your time on pen and paper, especially if it's a particularly nasty function.